Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll introduce you to Amazon Timestream, AWS's purpose-built time series database designed for IoT, DevOps, and operational analytics. We'll walk through the key concepts, including how Timestream stores and queries time series data, how dimensions and measures work, and how to write efficient queries. Let's get started. As modern systems become increasingly connected and instrumented, applications in domains like IoT, DevOps monitoring, application telemetry, and real-time analytics are generating massive volumes of high-frequency, time-stamped data. These workloads are characterized by continuous data streams that require high-throughput ingestion and low-latency processing, challenges that can quickly outpace the capabilities of traditional general-purpose databases. The core limitation is that relational databases weren't built with time as a central dimension. They treat timestamps like any other column, which makes time-centric operations like sorting by time, querying within specific intervals, or performing rolling aggregations inefficient and cumbersome. In contrast, purpose-built time series databases like Amazon Timestream are designed from the ground up with time as a first-class citizen, optimizing for both storage and query patterns that revolve around temporal data. Time series workloads also demand specialized query capabilities that go beyond basic filtering. These include rolling window aggregations, downsampling for dashboards, computing derivatives to spot trends, and even interpolating missing values. In a general-purpose database, these queries often involve complex joins, subqueries, and custom logic, whereas time series databases support them natively and efficiently. Another key factor is data lifecycle management. Time series data tends to lose value over time. For example, last-minute CPU usage is far more relevant than what it was a month ago. Time series databases recognize this pattern and provide built-in lifecycle policies that can automatically tier data from fast in-memory storage to lower-cost archival tiers, or expire it altogether, without manual intervention. Finally, time series data usually has a predictable schema and structure, repeating measurements from the same sensors, services, or systems. This makes it ideal for advanced compression and columnar storage techniques, enabling better performance and lower storage costs at petabyte scale. All of these reasons make a strong case for adopting a purpose-built time series database when working with workloads where time is the dominant dimension. Amazon Timestream is a fully managed, purpose-built time series database designed specifically for handling the scale, speed, and complexity of time-stamped data. Whether you're building large-scale IoT solutions, monitoring your cloud infrastructure, or capturing application telemetry, Timestream offers a high-performance, cost-effective, and operationally simple platform to ingest, store, and analyze time series data. One of the core strengths of Timestream is that it's entirely serverless. That means there's no infrastructure to provision, manage, or scale. AWS handles everything, from automatic scaling, high availability, and replication, to patching and maintenance, so your teams can spend less time on DevOps and more time delivering insights and features. A major differentiator is Timestream's automated data lifecycle management. You can configure retention policies that automatically tier data, keeping recent data in memory for low latency access, while older data is seamlessly migrated to magnetic storage for long-term retention at significantly lower cost. This approach ensures that your queries are always fast and cost-efficient, no matter the age of the data. At its core, Timestream provides a powerful SQL-based query engine that's optimized for time series operations. It supports advanced functions like rolling aggregations, interpolation, rate of change calculations, and time window filters, enabling developers and analysts to express complex temporal logic with simple, readable syntax. Under the hood, Timestream is engineered for high performance and scale. It can handle millions of writes per second, while supporting sub-second query latency, even when working with billions of data points. This makes it suitable for everything from real-time monitoring dashboards to historical trend analysis and machine learning feature extraction. Amazon Timestream provides the right combination of speed, scalability, cost efficiency, and ease of use for modern time series workloads, without the operational burden of managing infrastructure or databases. Amazon Timestream's architecture is purpose-built from the ground up to support the unique demands of time series data, offering high-throughput ingestion, low-latency querying, and intelligent data lifecycle management, all in a fully managed serverless environment. At the front of the architecture is the ingestion pipeline, designed to handle millions of time-stamped records per second from a wide variety of sources, including IoT sensors, application logs, and telemetry streams. This pipeline is highly parallelized and elastically scalable, ensuring that data is ingested in near real time without bottlenecks, even during peak loads. Once ingested, the data flows into a multi-tiered storage system. Recent data is stored in an in-memory cache, enabling rapid access and real-time analytics. As data ages, it is automatically migrated to a magnetic storage tier for long-term retention. This migration is governed by user-defined retention policies, which allow organizations to optimize for both performance and cost, keeping hot data accessible while archiving older records without manual intervention. Timestream's query engine lies at the heart of its analytical capabilities. Built specifically for time series workloads, it supports a rich SQL dialect tailored to temporal operations. Users can express complex queries involving aggregations over time windows, interpolation of missing values, and approximate percentiles with ease. The engine also seamlessly queries across memory and magnetic storage, with automatic indexing and partition pruning to maintain sub-second query performance, even when scanning billions of data points. Behind the scenes, Timestream automatically indexes dimensions and timestamps at ingestion time. It internally partitions data by time and other attributes, eliminating the need for manual schema design or tuning. This approach not only accelerates query performance but also simplifies development and operations. All of this is wrapped in a serverless management layer that takes care of provisioning, scaling, high availability, patching, and maintenance. Timestream ensures multi-AZ replication for durability and integrates with AWS services like IAM for fine-grained access control, KMS for encryption, and VPC for network isolation. Furthermore, Timestream is designed to integrate seamlessly with the broader AWS ecosystem. It connects easily with ingestion services like Amazon Kinesis, AWS IoT Core, and AWS Lambda, and supports visualization tools such as Amazon QuickSight, Grafana, and Prometheus. Let's walk through the architectural flow of Amazon Timestream, starting from how data enters the system to how it's queried by end users and applications. On the left, we begin with the data sources. These could be IoT devices, application telemetry, infrastructure monitoring tools, or any system emitting time-stamped data. Timestream supports integration through various methods, including file-based ingestion, REST APIs, and native AWS services like Amazon Kinesis, AWS IoT Core, and AWS Lambda. This makes it easy to bring in high-velocity streams of time series data from virtually any workload. Once the data is received, it passes through the ingestion layer. This layer is built to handle massive throughput, processing millions of records per second with low latency. It validates and indexes incoming data on the fly, capturing not only the time and measure values, but also dimensions, key value pairs that describe the context of each data point. From here, the data flows into the storage layer, which is split into two tiers. The in-memory store is designed for fast access to recent data, ideal for real-time dashboards and low-latency queries. As data ages, it automatically moves into magnetic storage, a more cost-efficient tier for long-term retention and historical analysis. This transition is governed by user-defined retention policies and requires no manual intervention, enabling seamless lifecycle management behind the scenes. Sitting on top of the storage layer is the query engine. This layer exposes a powerful SQL interface optimized for time series workloads. Users can run sophisticated analytical queries involving rolling averages, percentiles, time binning, and interpolations. The engine transparently accesses both storage tiers with built-in optimizations like partition pruning and indexed filters to ensure high performance, even when querying across billions of data points. Finally, on the right side of the illustration, we have the clients and applications that consume insights from Timestream. This could be dashboards in Amazon QuickSight, monitoring tools like Grafana, or custom applications querying Timestream through the AWS SDK or CLI. Regardless of the client, the architecture ensures secure, scalable, and low-latency access to time series data across the entire lifecycle. This layered, serverless design is what makes Timestream so powerful. It abstracts the complexity of ingesting, storing, and analyzing timestamp data at scale, so teams can focus on building data-driven solutions instead of managing infrastructure. In Amazon Timestream, dimensions and measures are foundational building blocks that define how your time series data is modeled, stored, and queried. Understanding the distinction between the two is essential for designing effective schemas and enabling fast, meaningful analytics. Let's start with dimensions. These are key value pairs that describe the metadata or context of a time series record. Think of them as the labels or tags attached to your data points, such as device ID, region, instance type, sensor ID, or application name. Dimensions are used to uniquely identify and group time series, and they play a critical role in filtering, aggregating, and organizing data for analysis. In fact, in Timestream, each unique time series is defined by the combination of its timestamp and dimension values. So for example, CPU usage from two different EC2 instances would be treated as two separate time series, distinguished by the host name or instance ID dimension. Timestream uses a schema-on-write approach for dimensions, meaning the dimension keys and their types must be consistent when records are written to the table. This consistency allows Timestream to automatically index all dimensions, enabling efficient query filtering and reducing scan times even across massive datasets. Each table in Timestream supports up to 128 unique dimensions, and all dimensions are stored as strings, regardless of the type of metadata. Now, let's look at measures. These are the actual values being recorded over time. For instance, metrics like CPU utilization, battery level, temperature, or response time are all examples of measures. Each record can contain one or more measures, and unlike dimensions, Timestream applies a schema-on-read model to them. This provides flexibility. New measures can be introduced dynamically without altering the table's structure, which is especially useful in evolving environments like DevOps monitoring or IoT telemetry. Timestream supports multiple measure data types, including Boolean, BigInt, double, and varchar, making it capable of modeling both numeric and categorical data effectively. Each table supports up to 1024 unique measure names, giving you the flexibility to capture a broad range of metrics within a single logical entity. Together, dimensions and measures provide a highly expressive and efficient framework for working with time series data. Dimensions give your data structure and context, while measures carry the actual signal or value you care about. This separation enables Timestream to deliver both modeling flexibility and analytical performance, making it a powerful tool for applications ranging from infrastructure monitoring to industrial IoT. When working with Amazon Timestream, writing efficient queries is essential, not only to ensure fast response times, but also to optimize your cost and resource usage as your data volume scales. Timestream is built around a range-restricted scan model, meaning that the more precisely you define what data you want through filters and predicates, the less data the system needs to scan, leading to lower latency and better performance. One of the most important best practices is to always include a predicate on measure name. This limits your query to a specific metric, like CPU utilization, memory usage, or disk I/O, which dramatically reduces the amount of data Timestream has to scan before performing calculations. Next, include a predicate on the time column. This might be a rolling window like last 2 hours or last 24 hours, depending on the use case. Since time is the primary axis in time series data, this kind of constraint is critical for keeping queries fast and focused on the most relevant slices of data. You should also include predicates on one or more dimensions, such as region, AZ, or hostname. This further refines the scope of the query and allows Timestream to target only the subsets of data you're actually interested in, avoiding unnecessary scans across unrelated time series. Another area to pay attention to is how you structure aggregations using group by. If you're grouping by high cardinality fields, like hostname or region, Timestream can better parallelize the query execution, which results in faster aggregations even when you're working with millions or billions of rows. Here's a practical example to illustrate all of these concepts. This query calculates average CPU utilization, along with the 90th, 95th, and 99th percentiles for a specific host over the past 2 hours. It groups the data by region, availability zone, host name, and 15-second time intervals buckets, using the bin time 15eths function to create consistent time buckets. This query is efficient because it includes all three key predicates: on measure name, time, and a dimension, host name. It also makes smart use of group by and built-in functions for percentile calculation to extract meaningful insights quickly and accurately. Amazon Timestream uses a serverless, usage-based pricing model, which means there are no upfront costs, no infrastructure to provision, and no long-term commitments. You simply pay for what you use, making it highly cost-effective for both small-scale and large-scale time series workloads. Billing in Timestream is broken down into three main dimensions. First, data ingestion is billed per million records ingested. This means that every record you write into Timestream contributes to your ingestion bill. However, Timestream supports a multi-measure record format, which lets you bundle multiple metrics into a single write. For example, instead of writing separate records for CPU, memory, and disk usage, you can combine them into one. This simple change can dramatically reduce your total record count, and by extension, your ingestion costs. Next, there's the cost of storage, which depends on the tier where your data resides. Timestream automatically stores recent data in a fast, in-memory store, which is priced at a premium because it supports low-latency, real-time queries. As data ages, it transitions to a more cost-efficient magnetic store, designed for historical analysis and long-term retention. You can configure the retention policy based on your use case, balancing performance and cost by keeping hot data in memory only as long as you need it. Finally, query costs are determined by the volume of data scanned, not the complexity of the query logic. So whether your query includes multiple aggregations, percentiles, or joins, the cost is unaffected, as long as it scans the same amount of data. This is where smart data modeling and query construction really pay off. Including predicates on time, measure name, and dimensions helps Timestream scan less data, execute queries faster, and significantly reduce your query spend. Additionally, Timestream takes care of indexing, data partitioning, and automatic tiering between memory and magnetic stores, all of which are managed behind the scenes and come at no additional charge. This means you can focus on your analytics without worrying about operational overhead or hidden costs. Monitoring in Amazon Timestream is designed to give you deep visibility into ingestion pipelines, storage health, and query performance, using familiar AWS tools like CloudWatch, CloudTrail, and integrations with observability platforms. Timestream emits detailed operational metrics directly to CloudWatch, making it easy to monitor ingestion throughput, query performance, and resource utilization. Key metrics include records ingested, rejected records, query count, query latency, and throttled requests. These metrics can be used to build dashboards, perform trend analysis, and trigger CloudWatch alarms for proactive alerting when thresholds are breached or anomalies are detected. You can also analyze query stats, such as data scanned and execution time, which are returned with each query to help optimize performance and control costs. Timestream integrates with AWS CloudTrail to capture API activity and access logs. This allows you to audit who queried what and when, monitor access patterns, and ensure compliance across your workloads. CloudTrail logs are particularly useful for security reviews, governance, and troubleshooting access issues. Timestream can also be used as a metrics backend for custom application telemetry. It excels at storing and querying high-resolution, time series data such as logs, IoT metrics, or DevOps signals. It integrates smoothly with tools like Amazon Managed Grafana, Prometheus, and CloudWatch dashboards, allowing teams to build rich, real-time observability systems. Additionally, the query history feature provides insights into past executions, helping with debugging, performance tuning, and governance tracking. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.